What is the second law of thermodynamics? But before that, as we have learned from our previous chapter regarding the first law, it's also focused only on the conservation energy that happen both in open and closed system. It also emphasizes that energy is conserved and no known process has violated this law. However, merely satisfying this law does not guarantee that the process will occur. For instance, there is a cup of hot coffee cooling in a cooling room adheres to the first law. However, there's a process where the coffee is hotter in the room, but it actually does not violate the first law. So this is when the second law of thermodynamics comes into the picture. Process inherently proceed in specific direction is what addressed by the second law. Second law also emphasizes that it must satisfy the first and the second law for the process to occur. So as the reverse process mentioned earlier, it actually violates the second law, which identified by the concept of entropy. Not only that, the second law of thermodynamics extends beyond determining the direction of the process. It also emphasizes in the quality of energy, unlike the first law that only focused on the quantity of energy. The second law focuses more on the quality as well as the quantity of energy. Most engineers are using second law to evaluate the energy, highlighting its importance in preserving the high quality of energy. We'll be watch more explanation about the second law of thermodynamics in system.
Thermal energy reservoir is a hypothetical body with a relatively large thermal energy capacity, which is mass times with specific heat, that can supply or absorb finite amounts of heat without undergoing any change in temperature. For example, the atmosphere does not warm up as a result of heat losses from residential buildings in winter. A reservoir that supplies energy in the form of heat is called a source, and one that absorbs energy in the form of heat is called a sink. Thermal energy reservoirs are often referred as heat reservoir since they supply or absorb energy in the form of heat. Irresponsible management of waste energy can significantly increase the temperature of portions of the environment, causing what is called thermal pollution. If it's not carefully controlled, thermal pollution can seriously disrupt marine life in lakes and rivers. However, by careful design and management, the waste energy dumped into large bodies of water can be used to improve the quality of marine life by keeping the local temperature increases within safe and desirable levels.
Okay, now so let's continue the second law of thermodynamic example with the example of refrigerator. Okay, as we all know that heat will never flow from cold to hot place, but in second law of thermodynamics says that work is required to pump heat from cold to hot place. So the transfer heat from the low temperature medium to high temperature one require a special device called refrigerator. Refrigerators are cyclic device, and the working fluid used in the refrigeration cycle is called refrigerant. So now let's look at this diagram of refrigeration cycle. As this refrigerant is pumped through the compressor, it will heat up and travel through this long S-curve and cool down over time. When the refrigerant goes through the decompressor, it's going to rapidly cool down. So now we have a very cold gas that slowly warms up as it goes around the curve. And eventually, the heat is going to be pumped from this room over the second room. So we're going to find one room that got really cold and the other room that gets really hot. Now let's look at the figure from our lecture note. This is the basic component of the refrigeration system and the typical operating condition. In a household refrigerator, the freezer compartment where heat is absorbed by the refrigerant serves as the evaporator, and the coil usually behind the refrigerator where heat is dissipated to the kitchen air serves as the condenser. So this is actually how the system looks like from the back of the refrigerator.
And now we move on to heat pumps. What is heat pumps? Heat pumps is a device that transfers heat from a low temperature medium to a high temperature medium. It has the same cycle as the refrigerator but differs in its function. The function is to maintain a heated space at high temperature by absorbing heat from a low temperature source such as well water and supply this heat to a high temperature medium such as house. The measured performance of heat pumps can be expressed in terms of coefficient of performance, COP-HP, defined as COP-HP equal to desired output over required output equal to QH over W net, and also can be expressed as COP-HP equal to QH over QH minus QL is equal to 1 over 1 minus QL over QH. A comparison with coefficient of performance of refrigerator reveals that COP-HP is equal to COP-R plus 1. There are two main types of heat pumps. The first one is air source heat pumps that extract heat from outside air and transfer it into a building to provide heating space. And the next one is ground source heat pumps, which extract heat from ground or a body of water and transfer it into building. The heat pumps are commonly found in residential, commercial, and also industrial setting. They play a crucial role in improving energy efficiency and reducing the environmental impact of heating and cooling system.
We move to the exercise 1, analysis of household refrigerator. The question is, a household refrigerator with a COP of 1.2 removes heat from the refrigerated space at a rate of 16 kJ per minute. Determine the electric power consumed by the refrigerator and the rate of heat transfer to the kitchen air. So this figure is the schematic of the question. So for A, the electric power consumed can be determined by using this formula, which is the power input equals to Q naught L over coefficient of performance refrigerator. So COP and removes heat of refrigerator are given by the question. So we just substitute into the formula, which is 16 kJ per minute over 1.2. So we get the 15 kJ per minute or 0.833 kilowatt. So for the B, the rate of heat transfer to the kitchen air can be determined by using the formula of the conservation of energy principle, which is Q naught H equals to Q naught L plus the power input that we get just now. So 16 plus 15 equals to 110 kilojoule per minute.
A heat pump is used to meet the heating requirement of a house and maintain it at 20 degrees Celsius. On the day when the outdoor air temperature drops to -2 degrees, the house is estimated to lose heat at a rate of 80,000 kJ per hour. If the heat pump under this condition has a COP of 2.5, determine A, the power consumed by the heat pump, B, the rate at which heat is absorbed from the cold outdoor air. For A, the question asks for the power consumed by the heat pump. We use the formula power net input equals to Q dot H over coefficient of performance for the heat pump. We can get the value for the Q dot H and COP from the statement given above. So we substitute the value 80,000 kJ per hour over 2.5 and we will get the answer 32,000 kJ per hour. So this is the full answer for A. For B, the question asks for the rate at which heat is absorbed. We use the formula Q dot L equals to Q dot H minus power net input. We just take the value for the power net input from the question A that we just calculate just now. We just substitute the value and we will get 48,000 kilojoule per hour. And this is the answer for question B.